Hey Analysis 2, this is Allison, Sam, and Steph coming at you with worksheet 4.4. So this is a proof of Rolle's theorem, which states that if f is continuous on the closed interval a to b and differentiable on the open interval a to b, and also that f of a is equal to f of b, then there must exist some value of c on the interior of a to b such that f prime c is equal to 0, which means the derivative is equal to 0. And we're able to use the extreme value theorem here without proof. So this proof is going to boil down to three cases. Case number one is that the function is simply continuous throughout a to b. Case number two is that there exists some value of c on the interior of a to b, such that f of c is going to be greater than or equal to f of a or f of b. And the only other thing that could happen is that there exists some value of c on the interval a to b, such that f of c is less than or equal to f of a or f of b. Our goal in this proof is to basically show that f prime of c is equal to 0 in all three of our cases, and thus we've proved that f prime of c must equal 0 forever, or for all values. Okay? Let's go ahead and look at case one. This says if f of x is consistent throughout the entire interval, then we basically are just looking at this. We're looking at a function from a to b that is constant. And we know that the derivative of any constant function is equal to 0. So I could put c anywhere in this interval, and I know for a fact that f prime of c is equal to 0. So I've got this case down, no problem. Case 2. There exists some value of c in a to b such that f of c is going to be greater than or equal to f of a or f of b. All right, so let's draw a picture here. What I'm dealing with is my interval a to b, and I've got my function value f of a and f of b. So f of a and f of b right here. And I have a closed interval here, right? I have a closed interval from a to b. And that is actually the one criteria I need in order to use the extreme value theorem. So the extreme value theorem is satisfied. And what that says now is that f has an absolute maximum and an absolute minimum, okay? Now, my absolute maximum and absolute minimum could occur absolutely anywhere on this graph, so I could draw anything I wanted to. I could draw something that looks like this. It needs to be continuous and differentiable, so it needs to be smooth, not have any jumps. And I can make any one of these c, because I'm trying to prove that there exists a c in the interval, not for all c's in the interval. So I pick c to be right here. I pick c to be my maximum, okay? This is f of c. And notice that this criteria is satisfied. F of c is larger than or equal to f of a equals f of b, okay? This criteria is satisfied. But here's the thing. If this is the relative max, then by problem 3 in our worksheet, which is right here, I'll put this right here, it says that if f has a local maximum at some value in the interior of an interval, then the derivative is equal to 0. This is it. This is our result that we can use. This is wonderful. That means that the derivative at that maximum is equal to 0, and I've got another case down. Okay? The last case is very similar. So I'm basically going to I'm going to put a c in the interval. So let's go ahead and draw my graph again. So this is a and this is b, and I've got my function value here. So this is f of a and f of b. And again, my graph needs to do something, whatever. It could look like anything, but let's make it look like this. I can make c anywhere, right? But I choose c to be my minimum. I choose c to be my local minimum. And this right here is going to be f of c. Notice that the criteria is satisfied. F of c is less than or equal to f of a or f of b. But here's the thing. Again, by using problem number 3, come back here, problem number 3. Thank you, problem number 3, down here. If f has a local minimum, which again, we can use the same argument as maximum, then the derivative must equal 0. So because I'm allowing c to be my minimum in this example, f prime of c is equal to 0, and my third case is done. So if we go back to the original proof, since f prime of c is equal to 0 in all three of these cases, then my conclusion must be true that f prime of c must equal 0. All right, hope that was clear and helped.